Hello, in today's video we're going to be discussing part 1 of section 6.3 on trig functions of angles. So first we're going to recall what it means for an angle to be in standard position. So we've got a triangle ABC, it's a right triangle, so that means that this was one of the acute angles, theta. We're going to place theta in standard position on the coordinate plane. Standard position means that the initial side is along the positive x-axis, so that would be here. So this is going to be my side AC. And then we rotate around counterclockwise. So that means that theta would be rotating up to the left, giving us the right triangle ABC that is in standard position. So we put theta, that angle theta, in standard position, and then we just connected B and C to create that triangle. So now that we've got our triangle in standard position, or our angle in standard position, we can talk about that point P at the end of the terminal side of angle theta. So we have our initial side where our angle starts, and then our terminal side where our angle ends. Point P has the coordinates x, y, where x is the distance horizontally that we moved to get to point P, and y is that vertical distance that we moved to get to point P. So if we are looking at the sine of theta, then sine in this triangle would be the opposite side over my hypotenuse. In this case, we'll call the hypotenuse r, and the reason that we do that is because eventually we're going to be talking about this angle theta swinging all the way around and point P coming with it to form a circle. So r would be the radius of a circle that we can form by rotating 360 degrees. So looking at theta, sine of theta would be the opposite side of this triangle, which is y, over the hypotenuse, which is r, so sine is y over r. My cosine is the adjacent side, the leg that's touching theta, so x over r. And tangent is the opposite side from theta, so that would be y over the adjacent side, which would be x. So tangent of theta is y over x. So we've got 6 trig functions. We've only introduced the first 3, sine, cosine, and tangent, but I'm going to go ahead back through and derive those ratios for sine, cosine, and tangent. So our adjacent side to theta would be x, that vertical side y, and then we call the hypotenuse r. Sine is opposite y over hypotenuse r, cosine is adjacent over r, tangent is y over x, or opposite over adjacent. Now cosecant is the reciprocal of our sine function. So that means all we are going to do is change the order of that ratio, and our y is now our denominator. So as long as y is not 0, then our cosecant is r over y. Secant is the reciprocal of cosine, so this would be r over x, again as long as x is not equal to 0, and cotangent would be x over y, and for both of these we've got some restrictions. Y can't equal 0 for cotangent, and x cannot equal 0 for tangent. And the reason that this is because we cannot divide by 0. We will get an undefined fraction. So example 1, we're going to use these to determine the value of our following trig functions. So cosine of 30 degrees. I'll put this angle in standard position. So here's my initial side, and my terminal side would be here approximately at 30 degrees. So I can drop this side down, creating a right triangle. And then I can use ratios of my 30, 60, 90 triangle to determine the cosine of 30 degrees. So in a 30, 60, 90 triangle, my hypotenuse is going to be 2x. My shortest side, which is across from my 30 degrees, is going to be x. And that remaining side is my middle length side, which is x times the square root of 3. So cosine would be the adjacent side, or the x side, over my radius r. So this is going to be x times the square root of 3 over 2x, giving me, when I reduce, a value of square root of 3 over 2. Sine of 45 degrees, I'll put this in standard position. Here's my initial side and my terminal side rotating counterclockwise 45 degrees. Again, I can drop that terminal side and create a right triangle. 45 degrees 45, 45, 90 degree triangles have the ratios of a, and then a square root of 2. I'm using a here to hopefully avoid confusion with the x's. Sine is then opposite, so 45 degrees, I want the leg opposite, which would be a, over my hypotenuse, which is a times the square root of 2. Reducing, I would get 1 over the square root of 2, and we can rationalize, which is what you're going to see most commonly done here. 1 times the square root of 2 is square root of 2, and then square root of 2 times the square root of 2 is the square root of 4, or just 2. So now what I'm interested in is the cosine of 150. If I swing around 150 degrees, going here is 90, all the way around is 180, so I'm going to start at my initial side, go 90, and then approximately here would be 150 degrees. Probably a little bit larger, but that's okay. Now I can't really make a right triangle out of this, so what I'm going to do is I'm actually going to drop that terminal side down to the closest x-axis, which would be that negative x-axis, to make a right triangle. Now we should know that rotating from the positive x-axis all the way to the negative x-axis is 180 degrees, so if that blue angle is 150, then that remaining piece of my angle is going to be 30 degrees. So now I can look at this triangle here, and what I'm trying to find essentially is the value of the cosine of this angle, 150, but I'm going to use what we call a reference angle to determine that value. So my cosine is going to be x, the value of x over the r, or the hypotenuse of this triangle. So my 30, 60, 90 triangle has a as the shortest side, and then a rad 3 as that middle side, and 2a as the longest. Shortest side doesn't look like my shortest side, but it is across from that smallest angle, so this would be a. I just drew it a little bit skewed. So cosine then would have a value of x, which would be a square root 3, but keep in mind here that we are on the negative x-axis, so this is going to actually be a negative x value. So negative a over the square root of 3 over my r, which is 2a. So I can reduce down to negative square root of 3 over 2. So my cosine in this second quadrant here is going to be negative because my x values are negative in that second quadrant. Now looking at sine of 135, we're going to approach this in a similar way. So I've got my initial side along the positive x-axis. 90 degrees would bring me to that y-axis, so 135 degrees would be about here, meaning that I would need to go another 45 degrees to make my full 180 degree rotation. So I will make a right triangle out of this 45 degree angle, and I know that the relationship of the sides of a 45, 45, 90 triangle are a and a for my legs, and then a rad 2 for that hypotenuse. So sine is the y value, which in this case would be a positive a, since y value is positive when we go up, over r, which is a rad 2. My a is reduced, giving me 1 over square root of 2, and again that will be equivalent to what we had before when we rationalized square root of 2 over 2. So what we are looking at in each quadrant is the relationship of your x and your y values to your radius, r. So in our second quadrant, since y is positive and sine is y over r, our sine will be positive. In the second quadrant, x is negative, and since cosine is x over r, our cosine will be negative. Reference angles. So let theta be in standard position, meaning that our initial side is on that positive x-axis. Our reference angle associated with that theta is the acute angle formed by the terminal side of your angle and the x-axis. So essentially, it's just how do we get to the x-axis in the quickest way. So if I have an angle in the first quadrant and I want to go back to the x-axis, the quickest way would just be to go back the way I came. So the reference angle would be equivalent to the angle itself in this case. In the second quadrant, to get to the x-axis, the quickest way is to keep going around to that 180 degree angle, just like our last example. So in the second quadrant, our reference angle is actually going to be that full 180 degrees minus our angle theta. If I take that full rotation and subtract out that red angle, we'll be left with our little blue reference angle. For our third quadrant, to get back to the nearest x-axis, I will want to go back, which means that I need to take my full angle theta and subtract off this 180-degree rotation. If I take this away, then I'll be left with our reference angle that brings us back to the nearest x-axis. And for our fourth quadrant, to get to that nearest x-axis, I can make a full 360-degree rotation and then subtract out that red rotation to be left with that little piece that's left. So here I would start with 360 degrees and subtract off my angle theta to be left with the reference angle. So all we are doing is trying to get to the x-axis in the shortest direction. So determine the reference angle for each of these two angles. I've got theta being 5 pi over 3. So I'll go ahead and plot this out. It might be easiest to turn this into degrees so that we have an idea of which quadrant it's in. So 5 pi over 3 multiplying by 180 degrees over pi. My pi's reduce, my 180 and my 3 reduce to 60 degrees and 1. 5 times 60 is going to be 300, and my denominator is just 1. So this angle is going to be 300 degrees, which would be between my 270 and my 300. So it's going to be in quadrant 4. So this is my angle theta, which is 5 pi over 3. I just turned it into degrees so that I know about where it is in my coordinate plane. So that means that my reference angle is going to be that remaining angle that gets me back around to a full rotation. In degrees it would be 360, but in radians it would be 2 pi. So if I want to know what that remaining reference angle is, I'm going to start with my 2 pi, so that full rotation, and then I'm going to take away the 5 pi over 3 to be left with just that reference angle. So 2 pi minus 5 pi over 3, I'll get a common denominator, 2 pi over 1 multiplying by 3's, 6 pi over 3 minus 5 pi over 3 gives me an angle of pi over 3. So this angle is my reference angle with a value of pi over 3. So this is one that we could then draw a right triangle with and calculate the values of our sine, cosine, and tangent functions. For our second angle, I've got 870 degrees. So I'm actually rotating around more than once. I've got 360 degrees, bringing me around back to where I started. I can then go another 360 degrees, and that brings me to 720 degrees. So from there, if I take away those two full rotations, then I need to rotate 150 more degrees, which would be between 90 and 180. So I am going to end my terminal side here in my second quadrant. So then since this angle is 150 degrees, my reference angle would be the remaining distance that I need to rotate to get to that x-axis, which is 180, which means that I need to go an additional 30 degrees. So therefore my reference angle is 30 degrees. So I'm going to use reference angle to determine the value of these couple of trig functions. So sine of 240, I'll start by plotting in my coordinate plane. My initial side is on the positive x-axis, and the terminal side is in quadrant 3, which is in between 180 and 270 degrees. So I'm going to go ahead and use reference angles. So going back to the x-axis, if this angle is 240, then I need to go back 60 degrees to get to that x-axis, giving me a 30, 60, 90 triangle, which has values of 2a and square root of 3a. But since y is negative in this third quadrant, that would be a negative square root of 3a. Sine is the opposite over the hypotenuse, so sine of 240 would be negative a rad 3 over 2a, which simplifies down to negative square root of 3 over 2. Similarly, for cotangent of 495, I plot the angle by first subtracting a rotation of 360, so I've got an angle of 135 degrees, which is in quadrant 2, and has a reference angle of 45 degrees, giving me a cotangent value of -a/a, or -1.